Today, let's talk about equations of planes. This will be important for us in Calculus 4 when we deal with the so-called tangent plane, which is the equivalent of the tangent line that we studied in Calculus 1 for objects which are 2- or 3-dimensional in nature instead of the tangent line approximating a 1-dimensional curve. By the end of today, we should be able to find the equation of a plane given a couple of different sets of information. We should be able to determine whether two planes are parallel to each other or if they intersect at a right angle. And we should be able to get some information in here related to what we covered yesterday and find a parameterization for the line that is formed when two planes intersect each other. Now, before we get started in today's material, I feel compelled to take a step back and remind us what a graph actually is. A graph of an equation is the set of all points that makes the equation true. For example, when we have the equation of a sphere, any point x, y, z on the graph had to satisfy the equation x squared plus y squared plus z squared equals 9 and be exactly 3 units away from the origin. So a point like 3, 0, 0 is on the graph because when we plug this point in, 3 squared plus 0 squared plus 0 squared equals 9 is a true statement. However, a point like 0, 0, 0 is not on the graph because when I plug in those values for x, y, and z, then I get 0 equals 9, which is not a true statement. Now, in general, a plane is just a flat sheet in 3-dimensional space, basically the 3D equivalent of a line. Now, because planes are to 3D as lines were to 2D, let's take a step back and think about what we know about lines in 2-dimensional space. Any line in 2-dimensional space could be expressed in one of two formats. The first was in so-called standard form, where you had some coefficient times the letter x, some coefficient times the letter y is equal to some constant called c. This was the standard form of a line described not in terms of a vector-valued function like we did yesterday, but in terms of a relationship between the coordinates x and y. There was also an analog to standard form where you had some number times x minus some initial x plus some number y minus some initial y equal to 0. This was a pretty convenient formula to use because this number x naught, y naught, these numbers corresponded to a point on the line. Now you may be thinking to yourself, okay, but there were some other formulas for lines as well. We had, for example, the point-slope form for a line, or the slope-intercept form for a line, and that could be used as long as your line actually had a slope. In other words, as long as your line was not vertical. But the two formulas given above work for any line of any variety in 2-dimensional space, even for vertical lines. Now, in order to prepare for what we're going to learn about planes, let's take a moment to study these two equations of a line further. And let's try and figure out the significance of the numbers a and b. What effect did different values of a and b have on the appearance of the line as graphed in 2-dimensional space? So as an example, let's consider the line 2x plus 3y equals 0. where we have a equals 2 and the coefficient of y is equal to 3. Now, in order to graph this function, you may find it helpful to rewrite it in slope-intercept form. A lot of people really like slope-intercept form. So we're going to take that 2x and move it to the right side, then isolate y, and so we get a slope of -2/3. So graphing this line, we can see that it passes through the point where x and y are both 0. We have a 0 intercept. And it also passes through the point where if we have rise over run, so if we run by 3 units, we rise by -2 units. So in other words, the direction of this line is given by the vector where we have final minus initial, final minus initial. A direction vector for this line points in the direction 3, -2. Now remember from when we did the dot product that if you wanted to find a vector which was perpendicular to a given 2D vector, one of the ways to do that was to first reverse the order of the components and then make one of the components the opposite sign of what it was before. So if I take -2 and 3 and I swap their position and I change the sign of -2, then we get a vector which was perpendicular to the direction of this line. We can see it graphically in a quick sketch here. Here's the vector 2, 3, which forms a right angle with the line that we're given in this problem. Now that 2, the x component, is exactly the same thing as the coefficient on x. That y component is exactly the same thing as the coefficient on y. So in general, what are we observing? For an equation where the coefficient of x is given by the letter a, and the coefficient of y is given by the letter b, the vector whose x component is the x coefficient and whose y component is the y coefficient is perpendicular to the line. Now let's store that observation in the back of our mind for a little bit, and let's talk about planes. Now the equation of an arbitrary line in two-dimensional space could be expressed in one of two forms, and the equation of a plane in three-dimensional space can likewise be expressed in a very similar format. It's just that because we're in three-dimensional space, we have a coordinate called z, and so we're going to include a z in our formula. So we can either write a number times x plus a number times y plus a number times z equals a number, or we can write a number times x minus some initial x, a number y minus some initial y, a number z minus some initial z equals 0. In the second case, the point x naught, y naught, z naught is on the plane in the same way x naught, y naught was on the line in the previous page. We examined the effect that the numbers a and b had on the graph of the line, so let's do some quick investigation to see what the numbers a, b, and c may signify for the graph of the plane. Now, for a simple example, let's just consider the xy plane. Now, the characteristic of all the points on the xy plane is that for all such points, the z component is 0. So I've sketched that plane in blue below. Now for z equals 0, we can think of this equation as 0 times x plus 0 times y plus 1 times z equals 0, which means that the coefficient of x is a equals 0, the coefficient of y is b equals 0, and the coefficient of z is c equals 1. And I've expressed that in this notation here. The vector ABC is equal to the vector 0, 0, 1. Now on this picture, let me go ahead and graph the vector 0, 0, 1. Notice something that's interesting about this vector. Because the plane is lying horizontally flat, and the vector 0, 0, 1 is pointing straight up, the vector 0, 0, 1 is perpendicular to the plane in all directions. What I mean is that the vector forms a right angle with the plane in the positive y direction, but it also forms a right angle with the plane in the positive x direction, and likewise in the negative x and the negative y direction. Now, what about a similar example? The characteristic of every point in the yz plane is that the x coordinate is 0. So let me sketch that plane in really quickly. This is the plane that's standing up with its front facing toward us. And this plane, the equation satisfies that the a value, the coefficient of x, is 1, b is equal to 0, and c is equal to 0. Now if I graph the vector 1, 0, 0 on this picture, then can you predict what's going to happen? The vector is going to face straight out toward us, and so as a result it's going to form a right angle again with this plane in every possible direction, both in the positive z and positive y directions, as well as the negative z and negative y directions, and any combination thereof. As a final example, we could also do the xy plane. The characteristic of any point in the xz plane is that its y coordinate is 0. So this is the plane that's standing up with its edge facing us. Now a is equal to 0 because there are no x's in the equation, b is equal to 1 since there's one y, and c is equal to 0 since there are no z's. And if I graph the vector in the positive y direction, then once again this vector is perpendicular to the plane in all directions. So what have we concluded? We concluded that the situation for the plane is extremely similar to the situation for the line. In the case of the line, the vector a and b, containing the coefficients of x and y, respectively, was perpendicular to the line in three-dimensional space. The vector ABC, containing the coefficients of x, y, and z, respectively, create a vector which is then perpendicular to your plane. Now to express this in formal terms, let's get some terminology established. The first thing that I want to talk to you about is a vector which lies inside a plane. We say that a vector lies inside a plane if it can be drawn with some starting position so that the entire arrow is inside the graph of the plane. For a quick example, we would say that the vector 0, 1, negative 1 lies inside the plane x plus y plus z equals 1. Now it can be difficult to graph a plane slash to graph any three-dimensional surface without using a graphing calculator or some other technological assistance. So let me go ahead and just plot a few points on this plane. For example, if x and y are 0 but z is equal to 1, then that satisfies the equation. So it is on the graph. Likewise, if x is 1 and everything else is 0, likewise, if y is 1 and everything else is 0, that point also satisfies this equation, so it would also be on the graph of the plane. So I'm just going to sketch in the triangle which passes through all these points with the understanding that this drawing only gives you a little portion, a little swatch, a little piece of the plane, and the actual plane is infinite. Now if I drew the vector 0, 1, minus 1, according to tradition, if I drew it starting from the origin, then the vector would not lie entirely inside the plane, because the plane itself never actually touches the origin. But if I grabbed the vector starting from the point at the positive z-axis, if I drew the vector with this initial point and then increased my y by 1 unit and decreased my z by 1 unit, then that vector would travel along this line segment on the plane from 0, 0, 1 to 0, 1, 0. So because this vector can be drawn with such a starting position that the entire arrow lies inside the plane, we say that the vector 0, 1, minus 1 lies inside the plane x plus y plus z equals 1. Now we can define a vector normal to a plane. In formal terms, this is what we would say. A vector is normal to a plane if it is perpendicular to every vector inside the plane. In informal terms, this means that the vector is perpendicular to the plane in all directions, just as we sketched when we were examining the xy, yz, and xz planes on the previous page. But the informal definition, although it is useful for us to get a graphical understanding of the situation, is not as useful for actual calculations as the real definition above. You see, we have the dot product, which allows us to calculate very easily whether a vector is perpendicular to another vector. We can just take the dot product of the two vectors and check whether or not the result is 0. In the case of the previous example exercise, we had a plane where the coefficient of x was equal to 1, the coefficient of y was equal to 1, and the coefficient of z was equal to 1. Suppose that I take the dot product of that vector with this vector 0, 1, minus 1, which lives inside the plane. Then I get 0, positive 1, and negative 1, whose sum is actually equal to 0, and therefore we know that the vector 1, 1, 1 is perpendicular to the vector 0, 1, negative 1, which lies inside the plane. Now the work that we have done up to this point, the exploration and experimentation, is evidence for the following fact/theorem. If you have a plane where the coefficient of x is equal to a, the coefficient of b is equal to y, and the coefficient of c is equal to z, then it is always true the vector ABC is normal to the plane. The vector ABC is perpendicular to every vector inside the plane. So as a quick example, let's find a vector normal to the plane 6x plus y plus 3z equals 2. This kind of question can be answered very quickly. All you have to do to find a vector normal to the plane is look at the equation, read the coefficients of x, y, and z, and use those coefficients to fill in the components of your normal vector. So the normal vector here would be the vector ABC, where the coefficient of x is equal to positive 6, the coefficient of y is 1, and the coefficient of z is positive 3. You're done. That's it. This vector is normal to the given plane. Now I want to point out something that's important about this idea of a vector normal to a plane. And that's that there are infinitely many normal vectors perpendicular to a given plane. For example, even with the very simple plane z equals 0, we have the vector 0, 0, 1. That goes one unit straight up and does make a right angle with the plane in every imaginable direction. But the same thing is true of a vector which is twice as long. 0, 0, 2 goes a bit further up, but it still makes a right angle with the plane in every possible direction. The same thing is true of a vector which points straight down even. 0, 0, minus 1. That also makes a right angle with the plane in every possible direction. So for this plane and for all planes, there are infinitely many possible vectors normal to the plane. However, they all have the following in common. All the normal vectors to a plane are parallel. They all do have to be parallel one to another. More often you will know what the plane's normal vector is, and you'll know the identity of a single point contained by the plane. If you have those two pieces of information, then you can find the equation of all the points on the entire plane. So all we have to do is use the fact that in the equation of the plane that has the form a times x minus x naught, b times y minus y naught, c times z minus z naught equals 0, the letters A, B, C represent the normal vector. And the x naught, y naught, z naught represents a point on the plane. So all we have to do is use the given information to fill in those blanks in the equation. We're given that the normal vector for our plane is 1, 3, 2. So those are the values of A, B, and C. We're told that the plane contains the point 1, minus 1, 3, x minus 1, y minus negative 1, z minus 3 equals 0. So in spirit, it's quite similar to finding the equation of a sphere, given information about the sphere's center and about the sphere's radius. In this case, because our object is straight and not curved, our equation doesn't have any squares in it. And instead of being given information about the sphere's radius, we're given information about the plane's normal vector, which describes its orientation, the way it's tilted and positioned in space. Now, as an optional step, you can simplify this if you're so inclined. But I don't consider this to be particularly important. So I'll do it once as a demonstration, and then I will leave it up to you to decide if that's something that you're interested in doing. In general, simplification is only useful in one of two situations, because it makes the next step in your calculations easier, or sometimes simplification helps you to be able to type in the answer without making any typos. Outside of that, simplification, generally speaking, is optional. So we can do a little bit of distribution. We can gather all of the variables on one side, all of the constants on the other. So 6 take away 3 plus 1 is 4. This would be another expression of the equation satisfied by all the points x, y, z on the graph of the plane. Now here is a general principle that I want you guys to keep in mind as you're working through the problems in this section. If you want to find the equation of a plane, you need a normal vector and you need a point on the plane. Now you may not be given a normal vector for the plane at the beginning of the problem. You may need to do some work in order to acquire that information. But in the end, if you're asked for an equation of a plane, you're going to have to get these two pieces of data at some point. I say again, normal vector, point on the plane. Those two together, you can find the equation. Exercise. A plane contains the two vectors 1, 2, minus 1, and 3, 0, 1. It also contains the point 1, 9, 7. Find an equation for the plane. Now, one of the essential pieces of information that we need has been provided to us. We have been given the point 190, which is a point on the plane. But as of this moment, we have not been given a normal vector. We have been given instead two vectors which are contained inside the plane. Which means that we still need to do some work to find the normal vector. So let's see how we might be able to find the normal vector given this information about these two vectors contained inside the plane. Now, by the definition of the term normal vector, the normal vector is going to have to be perpendicular to every vector contained in the plane. In particular, though, since we are given the vectors 1, 2, minus 1, and 3, 0, 1, we know for sure that the normal vector has to be perpendicular to those two vectors precisely. Now think back. What tool have we introduced that gave us a way to find a vector which was perpendicular to two given vectors? We could find such a vector by taking the cross product. The cross product of two vectors was perpendicular to both of the vectors that you used in the cross. So, here is our matrix determinant with ijk in the top row, 1, 2, minus 1, in the second row and 3, 0, 1 in the bottom row. Therefore, our vector has a component which is equal to the determinant of 2 minus 1, 0, 1, scaling I, minus the determinant of 1 minus 1, 3, 1, scaling j, plus the determinant of 1, 2, 3, 0, scaling k. Let's go ahead and calculate those numbers. We have 2 times 1, take away 0, that's 2. We have 1 times 1, take away minus 3, scaling j, and we have 1 times 0, take away 3 times 2. So we have the vector with 2 in the x component. This is 1 plus 3, negative 4 in the y component. And then we have 0 take away 6, negative 6 in the z component. This vector will act as our normal vector for the plane, perpendicular to the two given vectors which are inside the plane. So now, let's go ahead, use the information about the given point and the normal vector that we had to fill in the blanks for our answer. The normal vector is 2, negative 4, negative 6. X take away the given x, which was positive 1. Y take away the given y. Z take away the given z for the point on the plane. So this is the equation that is satisfied by every point x, y, z, which is contained in the graph of the plane. Here is another scenario. This time the plane is described to us in terms of 3 points that the plane passes through. Find the equation for the plane. Now in this case, we have an abundance of points that are on the plane, and we can use any one of them to fill the role of the point on the plane that we use for the equation. Which one you use is a matter of taste. It may give you an equation of the plane that looks different from the equation obtained by someone else who chose a different point, but the equations will simplify to the same thing, and you'll be exploring that in today's concept check, actually. But once again, in order to actually answer this question, we definitely need a normal vector. So how do we find a vector that's normal to the plane, giving this information? Now, we saw in the previous exercise how to find the normal vector if we knew two vectors that were contained in the plane. Then we could just cross those vectors, and the cross product would give us a vector that was normal. In this case, we're going to do a two-step process. First, we're going to find two vectors in the plane, and then we're going to cross those to find the normal vector. What we're going to use is the fact that because a plane is flat and straight, if we have points, which I will call P, Q, and R for short, if we have 2 points in the plane, then the vector that passes from one point to another is also in the plane. We saw that also in this middle example. The point 0, 0, 1 and the point 0, 1, 0 were both contained in the plane. Because of the linear nature of the plane, that meant that the entire line segment stretching from one point to another was contained in the plane, and therefore the vector, drawn here in orange, stretching from one point to the other, was contained in the plane. So using that idea, let's go ahead and find the vector. For example, maybe the vector stretching from the point P to the point Q, maybe the vector stretching from the point R to the point Q. Once again, many possible vectors can be calculated here. Many possible vectors can be calculated here. I have just chosen, basically at random, the vector that stretches from P to Q and the vector that stretches from R to Q. But you could just as easily use the vector that stretches from Q to P, or the vector that stretches from P to R. That hasn't been used at all. Once again, it might make your equation look slightly different at the start of your work, but it will be the same equation as someone else's after simplification. So based on my taste, based on my preference, let me go ahead and find the vector from P to Q. So the vector from P to Q, terminal minus initial, is 3 minus 2, 1, 1 minus 1 is 0, and 0 minus 3, which is negative 3. The vector stretching from R to Q, terminal minus initial, 3 minus negative 1, 1 minus 0, 0 minus 3. Having obtained those two vectors that are contained inside the plane, I can then cross them to obtain a vector normal to the plane. ijk, 1, 0, minus 3, 4, 1, minus 3. For the x component, we have the determinant of 0, minus 3, 1, minus 3. Then subtract the determinant of 1, minus 3, 4, minus 3. Then add the determinant of 1, 0, 4, 0. And we get, it looks like 0 take away minus 3. Then negative 3 plus 12 is 9. And then we have 1 minus 0, so that's 1. And so we have obtained our normal vector, 3 minus 1, 1. So using that, and using any one of the 3 points that we were given, we can say 3, x minus 2, for example. Negative 9, y minus 1, still using the first given point. We could do z, so negative 1, z minus 3, for example, equals 0. But there are lots of other choices that could be made. Depending on what vectors you chose, and in what order you decide to cross them, you might get a slightly different looking normal vector. You might get negative 3, positive 9, and negative 1 for the z component. Maybe you decided that you preferred to use the point 3, 1, 0. In which case you would have x minus 3, y minus 1, z minus 0. But you can rewrite one of these equations so that it looks like the other. Now, how do we describe the graphical relationship between two planes? Recall that we had some words and we had some language to describe the relationship between two lines. We said, for example, that two lines were parallel if they were pointing in, roughly speaking, the same direction. Potentially their positions were different, but their overall orientation was the same. We had a word to describe when two lines intersected at right angles. In that case, we said the lines were perpendicular. And we also had this term, the angle between two lines, to describe the graphical relationship between two lines in space. Similarly, we have some language to describe the relationship between two planes. Two planes are parallel if, roughly speaking, they are oriented or slanted in the same direction in three-dimensional space. But much easier in terms of actually checking whether two planes are parallel is to say that two planes are parallel if their normal vectors are parallel. As a really simple example, suppose that I had the xy plane z equals 0 versus a slightly larger plane 2z equals 3. The xy plane z equals 0 we know lies flat with the normal vector pointing straight up in the positive z direction. The plane 2z equals 3 is just slightly higher than that, so still oriented horizontally, just displaced slightly and moved up a bit. Its normal vector can be taken as 0, 0, 2 compared to the normal vector 0, 0, 1 for z equals 1. These two normal vectors are scalar multiples of each other. Therefore, the normal vectors are parallel. Therefore, the planes are parallel. This captures the fact that if the normal vectors point in the same direction or in opposite directions, then the planes are oriented similarly in space. We say that two planes are perpendicular if, once again, it's in terms of the normal vectors, if their normal vector are perpendicular. If you want to find the angle between two planes, then that is described in terms of the angle between the two normal vectors. Let's use this terminology to answer the following question, for example. Find a plane which is parallel to x plus y plus z equals 1, but which contains the point -3, 1, 7. As always, if you're finding the equation for a plane, you need a point on the plane and you need a normal vector. So where is this information about the normal vector in this situation? The information about the normal vector is hiding here where they say that our plane has to be parallel to this other guy. Of our plane must be parallel to the normal vector of this plane x plus y plus z equals 1. That normal vector is given by 1 for the x-coordinate, 1 for the y-coordinate, and 1 for the z-coordinate. Now, any vector parallel to 1, 1, 1 will do here. Once again, there is an infinite collection of possible choices for the normal vector to a plane. The simplest choice here for a vector which is parallel to 1, 1, 1 is to use 1, 1, 1 itself. Alright, so just picking the simplest possible choice, let's go ahead and plug in the normal vector where we have 1 times x minus the x of the given point, 1 y minus the y of the given point, 1 z minus the z of the given point equals 0. This can be simplified if you like, but it's optional. So now that we have some experience finding the equation of a plane, I would like to change track a little bit. And I would like to do a problem which exercises our understanding of equations of planes and parametric equations of lines. In this exercise, we're being asked to find a parameterization for the line where the two planes x minus 2y plus z equals 1 intersects the plane 3x plus 4y minus z equals 2. To make a quick sketch, which is not at all accurate or to scale or true to life or anything, this is a rough sketch of the situation that's going on in our problem. The question is, can we find a formula for parameterization for this line? Now, to find the equation of a plane, you needed two pieces of information. You needed the normal vector and you needed a point on the plane. And for a line, it was similar, wasn't it? For a line, you needed not a normal vector, but you needed a direction vector plus a point on the line. Now, to find this information, we're going to use the following two facts. We're going to use the fact, first of all, that this line, r of t, is contained in both the orange plane and in the pink plane. As a result, the direction vector for this line is contained inside both the orange plane and the pink plane. Because D lives inside the orange plane, D must be perpendicular to the normal vector for the orange plane. And the same thing is true for the pink plane. Because the vector D lies inside the pink plane, the vector D must make a right angle with the normal vector for the pink plane. That's what it meant to have a normal vector. So we're trying to find a vector D which is perpendicular to two given vectors, perpendicular to the two normal vectors. Can you anticipate what we're going to do in order to find D? Whenever you need to find a vector which is perpendicular to two given vectors, we use the cross product. The second thing that we're going to need to fill in the blanks of this formula is a vector r0, which points to a point inside the line. But any point inside the line must be inside both of the two planes. So it has to make both equations true at the same time. So to find a point that makes two equations true at the same time, we can solve a system of equations. Okay, so let's work on these two steps in order. First, let's work on finding the direction vector D by taking the cross product of the normal vector to the first plane. I'll call it n for normal. 1, -2, 1. And then the normal vector for the second plane, the coefficients are 3, 4, -1. So taking the cross product of the two normal vectors, in the order n1 cross n2, I have obtained a direction vector for the line, D equals -2, 4, 10. Now, just as with planes, we have a lot of different possibilities for the direction vector of a line. Any vector parallel to this particular choice for D will also work. It will get you an equation that might look slightly different, but when you graph the equation, the result will still be the same. Now in step number 2, let's see if we can find a point that makes both of these equations true at the same time. Now when you're solving a system of equations that has two equations but three variables, you have one more variable than equation. You have some freedom to make a decision. You are free to make a decision about the value of one of your variables. Now looking at this system of equations, it seems to me like y is the most complicated. So because I have one extra variable that's free for me to make choices with, I'm going to choose to make a choice and set the y value equal to 0. Choose because number of bars is greater than number of equations. Now when I make that decision that y is going to be 0, I'm left with a system that has two variables and two equations, just like we saw in algebra. X plus z equals 1, 3x minus z equals 2. And I can solve this system of equation using any of the algebra methods that I like. For example, this seems like a ripe opportunity for method of elimination. So I get 4x from adding the x's, add the z's, they vanish, add the constants, that's 3. That gives me x equals 3 over 4. And if I use that information together with this first equation, then I get x plus z, so 3/4 plus z equals 1, which implies that z is equal to 1/4. And we made the decision that y would be 0. So that gives us an r0, one potential choice of r0, which points to the location where x is 3 over 4, y is 0, and z is 1 over 4. Now there are an infinitude of other possible choices for r0, depending on how you decide to solve your equation. Maybe instead of choosing y equals 0, you choose to set y equals 1, or x equals 0, or z equals 0. So I'm a little bit short on space now. To finish this out, I would say the line where these two planes intersect, one possible answer for parameterization is the direction vector d that we calculated with the cross product, plus this one particular point on the line, which I found was 3 over 4, 0, 1 over 4. That concludes today's material. In sum, what have we done? We saw the general format for the equation of a plane. It was basically just a 3D extension of the two-dimensional equation of a line that we learned back in algebra. We saw how to construct the equation of the plane. In the end, all that you need to do is get information about one point on the plane and somehow get information about the normal vector for the plane. Once you have a normal vector and a point on the plane, you can just fill in the general template for the equation and get your answer. We also saw how to look at the intersection between two planes and parameterize the line where they intersect.